The administrative distance, or the AD of a route, is the trustworthiness or the believability of a route. In this example, we have a couple of different routing sources. Router R3 is learning about the 172.16.1.0/30 network from OSPF, and it's also learning it via EIGRP, and the question is, which one does it believe? Should it go via R1? Should it go via R2? Well, what R3 is going to do is consider the source. It's going to say, who sent me this information? And the routing source has an associated administrative distance. By default, a route that is directly connected, that's very believable to a router. So it has an administrative distance of a 0. If we go in and statically configure a route, by default, that has an administrative distance of a 1. However, we can make that a larger number if we want to when we're configuring the static route. But here we're dealing with OSPF and EIGRP. And if you take a look at the table, EIGRP has an administrative distance of a 90, while OSPF has an administrative distance of 110. Lower is better. EIGRP is going to be believed over OSPF. And you might also notice that there's an external EIGRP administrative distance of 170. External EIGRP is when EIGRP learns a route from an external source. Maybe we've redistributed an OSPF learned route into EIGRP. That route would then have an administrative distance of 170, but in this case, 172.16.1.0/30, it's being directly advertised by EIGRP. So in this case, based on administrative distance, R3 is going to prefer the route to 172.16.1.0/30 via router R2. At this point in our discussion, we're still generically talking about routing protocols. And when we're looking at the characteristics of a routing protocol, we might find that some routing protocols have a rule called the split horizon rule. Consider the topology on screen. Routers R1, R2, and R3, and you see their IP routing tables just below them, they know about directly connected networks. After all, their interfaces are participating in those networks. And let's say that they're using some routing protocol to exchange information with their neighbors. Router R1 tells R2 about the 172.16.1.0/24 network. R2 and R3, they each add that network to their IP routing table. R2 is going to let R3 know about the 10.1.1.0/30 network. That gets added to R3's routing table. Router R3 is going to educate routers R1 and R2 about the 192.168.1.0/24 network. And router R2 is going to let R1 know about the 10.1.4.0/30 network. And at this point, all of our routers know about all of the networks in this topology. However, some routing protocols, like EIGRP and RIP, they advertise the routing table that they're aware of to their neighbors. What would happen if R3 suddenly advertised the 172.16.1.0/24 network back out to R2? After all, R3 knows about that network. It's in R3's routing table. What would happen if it advertised that back out to R2? Well, R2 would see that and say, I need to update my IP routing table. I thought that was off of Fast Ethernet 0/0. Now it appears that this network of 172.16.1.0/24, it's off of interface Fast Ethernet 0/1. And R2 would update its routing table, and obviously that's wrong. R2 should not make that update. That is not the route to get to the 172.16.1.0/24 network. To prevent this type of thing from happening, let's put this back to the original state. To prevent this type of thing from happening, routing protocols like RIP and EIGRP, they implement something called the split horizon rule. The split horizon rule says that a router will not advertise a route out of an interface on which it learned that route. For example, in our case, R3 learned about the 172.16.1.0/24 network. It learned that route via interface Fast Ethernet 0/0. So R3, it will not be allowed to advertise that route, that network, out of Fast Ethernet 0/0. That would violate the split horizon rule. So this rule can help us prevent routing loops and prevent the corruption of our IP routing table.